Hello, thank you for joining. This is Mr. Carter. We're going to begin our exploration of ray diagrams, which are basically diagrams made to show where an image is formed in terms of mirrors. Okay, later on we'll look at lenses, but for right now we're going to focus on mirrors. Now, the first thing we ever draw is our primary axis. Our primary axis is a line right down the center of our page, basically. I've made this one a little bit low because the first mirror we're going to look at is a plane mirror. Now, my plane mirror, I'm going to draw straight up from there, and I'm going to make my primary axis be actually the ground. Okay, so I have this mirror. Now, to show which side of the mirror is which, it is customary to put in some cross-hatching. Okay? So these little crosshatch marks mean that this side out here is the side of the mirror where you would stand. This is the real world. And back here, this is behind the mirror. This is through the looking glass. This is the virtual world. Now, we will be getting around to some equations that govern where the images form at. And when we use those equations, any distances that are out here in the real world will be considered positive. And any distances that happen back here in the virtual world will be considered to be negative. Okay. Now, we're going to start off with a rendition of ourselves, okay, which we're going to draw very carefully as a stick figure, and I'm going to draw his shoulders down to some point. I'm making sure that he is on a line. The reason I'm using graph paper is so I can measure stuff easily. All right, so it doesn't have to be the best stick figure I've ever drawn. Okay, somewhere up here he's got some arms. Okay, and somewhere up here he's got a head. Now I want to make sure that his head is basically a 2x2 circle, okay, a circle with a diameter of 2. Very complicated stick figure. And now I'm going to be even a little stranger, and I'm going to say that he has one eyeball, and it is right in the middle of his head. Okay, I'm trying to make the world's most symmetrical stick figure because I'm going to try to recreate him in the virtual world. Now, if he looks at straight perpendicular to the mirror, he is going to see, well, his eyeball. So we expect someplace over there is his eyeball. Now, if he wanted to look at his forehead, he would have to look, well, halfway up from here, because the one thing that we already know about mirrors is that the angle of incidence, the angle of an incoming ray, is equal to the angle of reflection, the angle of an outgoing ray. Please do not confuse my minus sign here with a theta. So if he wanted to look at his forehead, he would have to look halfway from here to here. And so he would look from there to there as carefully as I can. Now I'm extending it out here for a reason. And then that would bounce back and strike his forehead so that he could see his forehead. Okay, and so he's going to see his forehead. Now, as far as he is concerned, the light traveling from his forehead looks like it's coming into his eyeball from over here someplace. Okay, now if he wanted to look at his right in between his feet, so we'll say right here at this point. All right. Then he is going to have to look halfway up from there. So I'm going to have to count boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 boxes to his eyeball. So it's going to hit halfway up over here for my upward angle from the normal to be equal to my downward angle from the normal. My incident angle to my refracted angle. Reflected angle. Refracted is when we get around to lenses. 1, 2, 3, 4, 5, 6. Okay, so it's going to hit him right here. So if he's trying to look at his feet, the midpoint between his feet, because he's Mr. Symmetry, then he is going to look here, and that's going to extend out there. As he looks at his feet down here, now I didn't try to draw in the normal before, and what's nice about graph paper is, look, I've already got the normal drawn in It's one of these lines. Okay, and what we said about the angle of incidence and the angle of reflection, this is the angle of incidence and this is the angle of reflection. Actually, now that I'm thinking about it, this is the light from his feet coming up to his eyeballs. That's going to change the two. That's going to change this to be the angle of incidence, because that's the incoming light ray, and the angle of reflection to be up there. Did that really change anything? No, because they're equal to each other. All right, now what we're going to find is that if this is the center of his feet, 1, 2, 3 boxes up, that's the top of his legs. We said his legs were like this. And up here where it meets, that's going to be the top of his head. Boy, my circles really stink when I do them by hand. And there's his eyeball. See, if he looked straight along this line, it's going to come straight back at him. It's going to look like it's coming along this line from his eyeball in the mirror. And so what we see, now if I wanted to, we could also draw a reflection to his arms, but we're just going to believe that his arms show up over there about the same size. So Mr. Symmetry sees himself behind the mirror at exactly the same distance. Well, let's check that. From here to here, this is the distance to my object. Mr. Symmetry is the object. From here to here is the distance to my image. Now, this one, the distance to my object is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 boxes that way is positive, because in the real world, 13 boxes. Could be 13 feet, could be 13 meters. I don't care. Right now it's boxes. And the distance over here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and it's behind it. So it's negative 13 boxes. Okay, so you look as if you are equal distant behind the mirror. And it's obvious to see that his height is the same. This is the height of my object. This is the height of my image. They happen to be equal to each other. I'm not going to bother counting boxes. Now, one set of boxes that I am going to count is the number of boxes from here up to here. Because really, did he need all this mirror? No, he didn't. He can see his feet with that much. He didn't even need this much mirror. How much mirror did he need? Let's see. Ooh, now I'm going to want to know his height. His height was equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 boxes. I had a feeling it was an odd number. So his height over here is 13. Oh, be careful here. In the virtual world, distances, horizontal distances, are negative, not vertical distances. This is still a positive 13. Negative 13 would mean that it was going down below this axis down here. All right, from here to here, 1, 2, 3, 4, 5, 6 and a half. And this is a common question that they like to ask you. If you wanted to see all of yourself in a mirror, how big does the mirror have to be? Well, how big is this compared to this? It's exactly half. If you have a mirror which is exactly half of your height, you can see your entire body. You do not need a full-length mirror on your closet door. Some people like it, but you don't really need it if you want to check out your entire outfit. You only need one which is half of your height. Okay, this comes into no other calculations. This is just a point of trivia which occasionally they ask you about. Okay. Let's see, what else do we want to have here? These are not magnified. They are the same size. Matter of fact, I'm going to introduce the equation for magnification now. Magnification is equal to the height of an image over the height of an object. If the image is bigger than the object, it's magnified, and it has a magnification which is greater than 1. It is also equal to the negative of the distance to the image over the distance to the object. Why do we need this negative? Because this is negative 13. negative 13 over 13 would give us negative 1. Well, that's not the same thing as 13 over 13, which, by the way, the 13s are completely coincidental here. These 13s are different from these 13s. They just happen to be how big I drew this thing. The negative cancels out this negative, so that my magnification is still positive. And that's something important. Whenever magnification is positive, if magnification is positive, that means that an image is upright. In other words, it doesn't look flipped upside down, okay, which is an important feature that we will see in a lot of different image calculations. Thank you for watching this first version of our ray diagrams.